Welcome everyone. Good morning and welcome to today's seminar. My name is Alain Dika, as you can see it's written. I'm delighted to be sharing this session. We appreciate you joining us for what promises to be a fascinating discussion on this topic, mathematical physics. So whether you are here as a researcher, student, or simply someone passionate about the field, we are glad to have you here. So once again, welcome. To say some few things about Frank before we start, before I hand over to Frank. Frank is currently pursuing his master's degree at the University of Cape Town, specializing in mathematical physics. His academic foundation is robust, with an undergraduate background in physics, applied mathematics, and statistics, which he completed in 2022. So despite being early in his research career, Frank has already made notable contribution to the field, publishing his work nationally in the SAIP 2022 proceeding and internationally in the Journal of Physics A, Mathematical and Theoretical Physics. So Frank's research has also been recognized and supervised and supported by the Oppenheimer Memorial Trust since 2024. So beyond academia, Frank is deeply invested in education and mentorship. He plays a crucial role as a committee member of the ESCOM Expo for Young Scientists and is a founding member of the South African delegation for the International Young Physicists Tournament, where he acts as a mentor and manager. He also leads a mathematical physics seminar at the University of Cape Town in the Department of Math and Applied Mathematics, which further fostering his intellectual exchange in the field. So today, Frank will be presenting on the PT-Symmetric reduction on the Ablowitz-Ladik equation. Frank, I would like to know, would you prefer us to interrupt you when we have questions, or should we keep the question and only up at the end?
That's a good question. I think asking questions during the presentation are fine. But if they require a longer answer, then I will probably postpone to the end. Yeah, so feel free to ask during the presentation.
Perfect. So we all got you. Frank, over to you. Thank you so much.
Fantastic. Thank you, Elaine. That was a wonderful introduction. Just checking, can everyone see the presentation?
Yes, from my side,
okay.
I can see your screen.
Fantastic. Okay, thank you. Yes, so as mentioned, I am Frank, and in this presentation, I will be talking about two very beautiful concepts in mathematical physics, namely parity times symmetry and integrability. And we're going to see how this can be applied in the context of optics. So the title is quite technical, but our objective will be to construct networks of optic fibers with gain and loss. So, parity times symmetry refers to systems that are invariant under a combined PT operator. Right, so what does that mean? Parity, if you're in physics, you will be familiar with this. So it's an involutive spatial reflection. Usually you talk about, okay, if you have a space vector x, then you reflect it, right? So you reflect it to minus x across the origin. But you can be more general. Parity can be any spatial reflection as long as it satisfies the condition p squared equal to unity, right? And then time reflection refers to a unitary time reflection, right? So you're reversing the flow of time. And this particular symmetry attracted a lot of attention in non-Hermitian quantum mechanics. So Bender and Butcher posed a challenge to the fundamental postulates of quantum mechanics. Sorry, that's in particular, the postulate that Hamiltonians should be Hermitian. So, right, usually you assume that H dagger has to equal H if H is your Hamiltonian. But it turns out you can generalize this. You can consider a wider range of Hamiltonians that are PT-symmetric and still have real spectra. This is in the quantum context, but it turns out you can also advance that analysis to classical mechanics, where it allows you to talk about systems with balanced gain and loss. So we will talk about PT symmetry in the quantum context and then adapt it to optics. So let's consider a wave function governed by a non-relativistic Hamiltonian, right? Where Vx is our potential, right? And we deal with a standard Schrödinger equation. Then let's define the parity and time operators. So P reflects across the origin, and then time reverses, right? So time operator reverses time, but it also applies a complex conjugate. And the reason for this is that you have to preserve the Heisenberg algebra, right? So if you consider the commutator of x hat and p hat equal to IH bar, in order for this algebra to be maintained by the time operation, you need to also have it apply a complex conjugation, right? So PT symmetry is just a statement that the Hamiltonian commutes with the PT operator. Okay, so PT symmetry generalizes the hermiticity. So the dagger operator is a PT symmetric operator, but PT symmetry allows you to extend beyond this. And with a lot of math, you can show that PT symmetry is a necessary but not sufficient prerequisite for real spectra. And you can see this in a very simple example. What we're going to look at are two quantum boxes. So here is a closed space, right? This is some closed system that we're dealing with, and we say, okay, let's add some probability flow to that box, right? Add some proportional gain to your system. This system is not PT symmetric because there's no time reversal going on, and it's not very interesting because if you just add probability flow to this, all that's going to happen is your probability will explode, right? So that's not physically interesting. The way you make the system PT symmetric is you make a copy of your system and you reverse the flow of time. So now instead of having gain, you have loss. But this system is not interesting either because you simply have probability decaying to 0 in this box. All right. What is interesting is when you couple the two systems, right? So you have some interaction between the two models. And if you have a sufficiently strong coupling strength G, then at some point, the probability flow will be conserved. So we can observe this in a simple two-dimensional system, right? Where we define a vector psi, and we're going to call this, the first element is, our gain box, and the second element is our loss box, right? And we're acting on it with this 2x2 Hamiltonian, where the plus I gamma, that corresponds to the gain, and minus I gamma corresponds to the loss, right? And the parity operator is simply exchanging the two spots. So that's a kind of reflection. And let's check, is the system PT symmetric? Well, firstly, the time operation simply applies complex conjugation because it's time independent. And then applying the parity operator, you swap the two spots, right? The I gamma and the minus I gamma. And this is clearly equal to the original Hamiltonian. So it's PT symmetric, right? And you can trivially solve for the eigenvalues. And this gives you plus minus square root of G squared minus gamma squared. So there's interplay between the coupling and the gain loss parameter gamma, right? So If gamma is smaller than the coupling, then you have broken PT symmetry, right? So the eigenvalues become complex, and your solution either decays or explodes. However, if oh, sorry, am I writing this wrong? Gamma exceeds the coupling, then the system explodes. Sorry about that. If gamma is smaller than the coupling, then we have a system that is controlled. The energies are real, so the system is conserved. Right. So that is for a simple two-dimensional system, right? But you can really, there's a lot that you can do in quantum mechanics with PT-Symmetry that extends beyond what we're studying here. This is for those who are in quantum mechanics and quantum field theory. It's very interesting to look, for example, at the quantum mechanical postulates because you need to make a lot of modifications there. You can also talk about deformed quantum field theories, so your phi-3 and phi-4, and it even extends to quantum electrodynamics and gravity. So it's really quite a deep topic with a lot of interesting mathematics. What we are going to focus on is the jump from quantum to classical systems, right? So the way we're going to do this is that, okay, back in the late 1990s, PT-Symmetry gained focus in quantum mechanics, but shortly after, it found extensive theoretical and experimental application in classical optics. And the reason for this is the paraxial approximation. So what we're going to do is we're going to look at an optical medium with electromagnetic waves traveling through it and show that you can derive a quasi-Schrodinger's equation. So let's consider an electromagnetic wave that is traveling along a fixed axis through a medium with some refractive index. All right, so wave is traveling upwards, but then you have a refractive index nx that varies along the x-axis, right? With minimal displacement. So the electric field satisfies a Helmholtz equation where k of x depends on the refractive index explicitly. And what we're going to do is we assume very small deviations of the refractive index from some constant value, right? So for glass, we can take the base refractive index to be something like 1.5, and then nu of x is our perturbation, which we assume is much smaller than 1, right? We then look at the electric field and say, okay, we're going to strip off the main z dependence of the wave and instead look at an envelope equation that depends on x and z. So you substitute that in, and you get some nasty equation, but you make some simplifications. In particular, you assume that the z dependence of your envelope is much less than its dependence on the x-axis, right? Because we've stripped off the main z dependence. So if you apply that approximation, you end up with a Schrodinger equation for electromagnetic waves, right? So instead of having time evolution, we can think about the wave as evolving along z, right? So this is our time axis, and our potential has been replaced by this function for the refractive index, right? So this is a potential. But the crucial difference between quantum mechanics and optics is that in optics, you have no requirement for probability conservation. You can have a complex potential, and that's completely fine, right? Because in optic fibers, you can have gain, you can have loss, and that is completely physical, right? So if nu of x is greater, if it has a positive imaginary component, that corresponds to gain, and if there's a negative imaginary component, that corresponds to loss. And then PT symmetry applies a constraint on what that refractive index can look like. And this is this is really remarkable because it actually shows up in experiment. And we're going to look at a system called the PT-Symmetric dimer. And this is where PT symmetry breaking was first observed experimentally. So what we're going to do is we're going to start with this Schrodinger equation and discretize it. So we take x and write, okay, we're just going to consider 2 points, right? And relabel our new wave function or our envelope function, right? To u and v. And this is kind of the simplest dimer that you can come up with, right? So there's gain in one optic fiber because u dot is proportional to gamma u, right? So that's our u node. And then in the other slot, we have minus gamma v proportional to v dot. So that's where the loss is occurring, right? So when we discretize, you can think of the individual points as corresponding to optic fibers, right? You've got gain, you've got loss, and then the interaction terms correspond to evanescent coupling. So if you recall from electromagnetism, when these waves bounce off the interface of the optic fiber with the outside, right? So if you have a wave hitting here, there's an evanescent wave that protrudes out and interacts with the other optic fiber. It's a very weak interaction, but it is there. So we assume that it's a linear interaction, right? So this system is pretty much identical to the Hamiltonian that we just considered, right? Because we can write this in the form I u dot v dot equal to I gamma 1 minus I gamma times u v, right? So this is our Hamiltonian in quotes. So this system is pretty similar to what we've already considered. So you can solve for the stationary solutions and obtain what we now call a growth rate instead of the eigenvalue. And clearly, if the gain exceeds some cutoff value, the system explodes, right? Because the growth becomes exponential. And this is not desired, right? You can think about this as an optic fiber where a light wave is traveling through and the system, the total optical power is just increasing without bound. And you don't want that. So you want to come up with a way to actually arrest the growth of the trajectories. And the way you can do this is by introducing nonlinear terms, right? So let's see, how can we do that? In optical systems, you can naturally include a cubic term, self-interaction due to the Kerr effect. So in this case, the refractive index becomes a function of the optic power, right? So if you increase the optic power, then the refractive index changes with it. And if you add these terms to your model, you end up with what's called the PT-Symmetric standard dimer. So all we've done is add some Kerr nonlinearities. And it turns out that this system is bounded. The solutions do not actually blow up. So why is that? And the short answer is that we are bounding the trajectories. So the idea is to identify conservation laws that confine the accessible phase space. So for dimers, we can exploit what's called the Stokes transformation. So these are real quadratic combinations of u and v. And this gives you a system of real equations in terms of what are the Stokes variables, x, y, and z, and r. And then this gives you access to standard methods of ordinary differential equations. So you can recover two conservation laws. So you can do this by inspection. Let's see how to do this, right? So we've converted our system to Stokes variables, and we have, for example, x dot equal to yz, and y dot equal to 2 minus x times z, right? Where we're at x dot equal to dx over dt, right? So you can take a quotient. and you get rid of your z, so that's y over 2 minus x. And if you cross these out, you end up with a separable equation, right? So it's dx over dy equal to y over 2 minus x. And this is trivial to solve. So you end up with c1 equal to x minus 2x plus y squared, right? And the point is that in your Stokes vector space, what you then have is a cylinder in the phase space. So let's put in our axes. Let's make this x and make this y, add a z-axis. And the point is that our trajectories are now constrained to a cylinder. Okay, and this just kind of continues down. And the second conservation law then adds a further constraint. And this is what bounds the trajectories, right? So imagine there's a second conservation law, and this induces some manifold that intersects with the cylinder, right? So what you end up with is a system where all your trajectories are restricted to bounded manifolds of the phase space. So the standard dimer, it doesn't have any, it doesn't experience any blow up. You can have an arbitrary gamma. You can put in as much gain and loss as you want, and the system will remain stable. So this is fantastic. This means it's a nice system. It's a physical system. And this kind of leads into the main thrust of the work that I'm doing. The best way to ensure that the PD symmetry is restored, so the easiest way to prevent this blow up, is to ensure that your system is integrable. Now, we've talked about PD symmetry. What is integrability? Now, when I talk about this, I'm referring to Hamiltonian or Liouville integrability. Sorry, let me just try that again. And for a system to be Hamiltonian integrable, you need to satisfy a couple of criteria. First, your system needs to be Hamiltonian, and all the systems that we've looked at are Hamiltonian systems, quantum and classical. But you need a lot more than that. If your system is n-dimensional, then you need n conserved charges along with that. So for the standard dimer, we have two coordinates, right? U and V, and we found two charges, C1 and C2. Okay, so we have two charges, but we also need to show that the charges can meet with each other, right? So that is a statement that, okay, if you've got some Poisson bracket for your Hamiltonian system, then commutator of C1 and C2 equals naught, right? And the final statement is you need to show that these charges are linearly independent. So if all of this stuff holds, then by Liouville-Arnold theorem, you can solve the system by a canonical transformation to action angle variables. So you can take a nonlinear system and essentially unfold it into a system that evolves in a linear way. And the solutions are constrained to tori, right? So it's bounded. So intuitively, integrable systems force regularity and solvability of the trajectories by inducing this really fixed geometry. And it gives us quite a lot because it doesn't just bound the trajectories. It allows us to actually solve the system in its entirety. So this is a really nice property to have. And a lot of fundamental systems that you use to talk about physics are integrable. So to kind of just make it less abstract, examples of integrable systems are a nonlinear pendulum, right? So just a pendulum on a bob. That is an example of an integrable system. If you're in astronomy, you also deal with the Kepler model, the two-body problem, if you've got the Earth going around the sun. That is also an integrable system, right? So it's actually not that abstract. The point is these systems both satisfy the Liouville integrability criteria. So a simple example is the standard dimer. And here I just want to demonstrate, how to construct the Hamiltonian by inspection. Right, so here we're going to turn off the gain and loss, right? You can construct the Hamiltonian for the standard dimer, but it is incredibly complicated. So let's look at this, right? We have a standard Poisson bracket. So in classical mechanics, this is what's called the standard Poisson bracket. And the point is here you can write down the equations and reconstruct the Hamiltonian from those equations, right? So the point is we know what the equations of motion are. So we write, okay, I u dot equal to v plus u squared u squared v. But we have that it's, we want to find the Hamiltonian that generates the system. And we know that the Hamiltonian satisfies these two conditions. Partial q bar and partial v bar. So the point is you can use methods from first year to integrate over this, and you end up with a Hamiltonian, which depends on u bar, v, and v bar. And this is equal to u v bar plus its complex conjugate plus some nonlinear terms, quartic terms. Right. So with systems like these, everything's still nice. You can find the conservation laws by inspection. You can compute the Hamiltonian by inspection, right? And it turns out that you can use this approach to find a whole wide range of PT-symmetric dimers, right, with gain and loss, that are completely integrable. They have a Hamiltonian, and they have conservation laws that lead to integrability, right? So that we know how to do. What we don't know how to do is deal with the high dimensional case. So oligomers are high dimensional dimers, right? So previously we dealt with U and V. What we're interested in, and the question we kind of asked is, what happens if you add a third node, right? So what we're doing here. Firstly, can you add additional nodes to the system? And second, can you show that such a system is integrable, even if there's gain and loss added to the system? And the short answer is that it's actually really difficult to show this. There are no known systems of this kind, right? Which is strange. We should be able to do this with a slightly larger system with 3 or 4 optic fibers. But when we started looking at this, there wasn't really anything that looked like that. So how do we actually do this? How do we construct such a system? And the way we went about this was to start with the Ablowitz-Ladik equation as a base model. So the idea is we start with an optic fiber model that we know is integrable, but doesn't have gain and loss. And then we deform it by adding PT-symmetric terms. And the Ablowitz-Ladik equation is fantastic. It is integrable for an arbitrary size. And it uses quite an interesting canonical bracket to make the system nonlinear. So you'll see here that this Hamiltonian is quadratic, so it doesn't seem like it's a nonlinear system. But you define what's called a GIK Poisson bracket. And when you generate the time flow, you end up with a nonlinear system. So there are these nonlinear interactions between nodes. So imagine you have an optic fiber Qn, and then Qn plus 1 and Qn minus 1 neighboring. Then the point is that there's nonlinear interaction between these neighboring nodes. Okay. So we want to deform the system to make it PT-symmetric. Although actually the system is PT-symmetric, but not in a useful way. The point is it is PT-symmetric, but with a parity operator that is simply the unity. So it has a trivial parity transformation. We want to find some deformation of the Ablowitz-Ladik where the parity is non-trivial. So we started simple by deforming a low-dimensional Ablowitz-Ladik equation. So we start with 3 nodes, U, V, and W. And we chose some PT-symmetric deformation in the Hamiltonian. We just said, okay, let's add a plus I gamma in here. You define a parity transformation, and this is like a reflection. You keep V intact, but you interchange U and W. And with that operation, you end up with a parity time symmetric system. On top of that, you find two additional conservation laws, right? So the Hamiltonian, total energy, fine. Momentum, also conserved. And also conserves this capital N, which is, I call it departure norms. It's not really the total charge, but in this kind of, with respect to the brackets, it's a type of charge. So that was good. We showed that this system is integrable. And in fact, you can generalize it to an arbitrary size. So you consider a lattice with some finite number of nodes and an arbitrary set of perturbations, PT-symmetric perturbations. So these theta n are our PT-symmetric terms. And you keep the same canonical structure as you did for the base of Ablowitz-Ladik. It looks complicated because you have all these theta n's, but you can apply a non-uniform Gauss transformation to yield a uniform lattice. So instead of all these theta n's, you can just keep track of a single parameter, capital theta, right? So this is critical. This is what makes it PT-symmetric. And the way you can think about this system is a network of optic fibers that have been connected into a cylinder, right? What's kind of missing here is that Vn plus 1 equals V of minus n. So that's the periodicity condition. And what the theta term does, what the PT symmetry does, is it corresponds to a twist of the optic fibers around the axis of propagation. So this is a good start. We have this Hamiltonian system, but we need more, right? So the system that I've written down here is 2n plus 1 dimensional. So we need 2n plus 1 conserved charges, right? And obviously you cannot obtain these by inspection. That's the first problem. And the second problem is you also need to show that those conserved charges commute with each other, which is a massive task. So what this suggests is that we must find some kind of generating function for the conserved charges, and we need a systematic way to ensure commutativity. So if we find, first we find, a set of charges such as their time derivatives are 0, and we need to show that if we take the commutator in terms of the epsilon brackets, everything must commute. And the way to go about this is to introduce the lax formalism. So we start with the equations of motion and express it in an abstract form called the lax representation. So here we are moving on from PT symmetry and going into detail on integrable systems theory. So what is the lax representation? We're moving away from the equations of motion for just a moment, but now think of assigning a bunch of auxiliary vectors to each point, to each lattice point, right? So each lattice has a 2 vector, psi n, right? So it looks like this, psi 2 of n. And right, this is assigned at each optic fiber. And we associate 2 linear problems with it. The first is what's called the space lax problem. So we define a space lax matrix, UN, space lax matrix. And this guy's job is to map psi n to psi n plus 1. So if we start at a node here, then UN maps us to the next auxiliary vector. All right, that's the space problem. And then simultaneously, you're dealing with a time problem. So you have a time lax matrix that governs the time evolution of the auxiliary vector. And you can think of these as derivatives, right? So Vn is our stand-in for a time derivative, and Un can be viewed as a space derivative. So what we kind of want to impose on these matrices is that they satisfy a mixed derivative condition, also known as a zero curvature condition. So it's almost like we're saying, okay, we've got some alternative version of time and space derivatives, and we want the order of operations to be the same, right? So if you consider time derivative and x derivative of f, some other function, we want the order to not really matter, right? And this is what we're doing with the matrices. We apply a zero curvature condition. If we apply the one matrix followed by the other, that should be the same as the reverse order. And this is what we get. This is a zero curvature equation. And this is the point where we link the abstract formulation to our actual system. If you choose un and vn in a particular way and evaluate this zero curvature condition, you can ensure that firstly it holds, the zero curvature condition holds, but you can also choose capital Un and capital Vn such that that matrix equation gives you the equations of motion on the previous slide. Right. So kind of the critical question here is, what does this actually give us? And the short answer is that the space lax matrix is going to give us the conservation laws, but we're going to focus on the conservation laws, right? So we need to do a little bit more work. First, we design or we construct a monodromy matrix. So this is an ordered product of all the UNs. Hi, is there a question?
Frank, yeah, can I ask a quick question about the previous slide?
Sure.
This lax representation, does not look very obvious to guess. Was it kind of known from before for the standard Ablowitz-Ladik, and then you just have to figure out how do the thetas enter the game?
Yes, that's correct.
Okay. But that was kind of known from before, I guess, because it looks at first sight almost impossible to guess such a.
Yeah. No, that is quite an important observation. And yeah, it's not obvious to guess at all. And what I'm not mentioning in this presentation is that there is actually a way using methods of R matrices to, right, if you start from the capital UN and create the Hamiltonian from that, you can actually construct the time lax matrix from knowledge of the Hamiltonian and the space lax matrix. So it's actually, you don't actually have to guess. It's not easy to do it, but you can generate the capital Vn.
Okay, thanks. Okay, that's interesting. Thanks.
Sure, thank you. This is a very good question. Right, so where were we? So right, we've got our space lax matrices, and our next step is to construct what's called the monodromy matrix, which is kind of like a monodromy matrix in the context of ODEs. So imagine you have a vector psi in, at this node. Then obviously applying UN takes it to psi n plus 1. You repeat that action over and over and over again. There's a periodicity condition, and the point is TZ takes you all the way back, right? And that's what that object is. That will carry our conserved charges. And then the second object that we need is what's called the ultralocal R matrix relation. So you define Poisson algebra between the lax matrices, and you define what's called an R matrix, which defines the algebra between the UNs. And this object's purpose is to prove the commutativity, to show commutativity. So from the monodromy matrix, you construct what's called the transfer matrix. So if you take the trace of your monodromy, you end up with a Laurent expansion, right? So what I've only kind of hinted at is that there's the spectral parameter that we've introduced. And the purpose of the spectral parameter in this physical context is essentially to separate out these coefficients, right? So the QI, these are functions of your fields, the UI and UI bar. And this is our generating function. So why is this the case? The non-trivial statement is that the fundamental R matrix relation leads to the condition that the transfer matrix commutes with itself for different values of this spectral parameter that we've introduced. And an immediate consequence is that the coefficients commute with each other. So we have a bunch of commuting charges, which is one part of the Liouville integrability, but we haven't shown that they're conserved. What you then do is you appoint a Hamiltonian. You say, okay, I'm going to define a Hamiltonian as some function of the conserved charges, right? So we find in the expansion two quadratic terms. What I mean by that is that, okay, Q2 equals a sum over the fields, right? So UI minus 1 bar, n equals 1, 2, n equals, sorry, n equals minus n to n, plus the periodic term. And then Q2 bar is just the complex conjugate of that charge, right? So if you construct the Hamiltonian in this way, this Hamiltonian is precisely the Hamiltonian of the uniform lattice at the very start. So what this means is that by construction, you have a Hamiltonian that generates the equations of motion for the uniform lattice. And this Hamiltonian, by virtue of being constructed out of these commuting charges, it commutes with everything, right? So there's a bunch of conservation laws associated with your system. And we know they commute. And you can also show that they're independent, linearly independent. And that constitutes the proof that the system is integrable. So that's fantastic news, right? We have this integrable system and it has non-trivial PT symmetry. But we wanted to go a little bit further than this because there's a bit of a problem that the system is Hermitian even in the linear case, right? So previously we talked about dimers that blow up in the linear regime, but then in the nonlinear regime, we have a restoration of the PT symmetry. But for this system that we've constructed, there is no blow up even in the linear regime, right? So the point is the linearized operator is clearly Hermitian, right? So if we call this H, you can clearly show that H dagger is equal to H, right? So it's not clear if this PT-symmetric system induces any sort of dynamic bifurcation. So our follow-up question was, can we find a PT-symmetric system where the dynamical properties are less subtle, right? So we look for a system where the linearization is non-Hermitian, right? So if we linearize the model, we want to end up with H such that H is not Hermitian, right? Okay, so there's blow up. And then the nonlinear terms restore the trajectories, right? So the way that you do this is you extend beyond the kind of typical integrable structure and open up the boundary conditions. So you can incorporate, for example, Robin boundary conditions using what's called the double row monogamy and transfer matrix formalism. So you define a monogamy matrix that works a little bit differently. So previously, the monogamy matrix mapped all the way around, right? So if we start here with psi n, we kind of map all the way around. Instead, we construct this new monogamy matrix. It starts here, right? Let me make that slightly clearer. It starts here. It transports all the way to the final node. Then it hits a K minus, right? So that's the reflection matrix. Goes all the way back, hits a K plus matrix, and then starts, ends where it started. And kind of the implication here is these reflection matrices define the boundary conditions. And these K matrices have to satisfy a set of what are called reflection equations. And this eventually ensures that if you construct a trace of your double row monogamy, you end up with a similar condition to what you had before. You construct a transfer matrix that sum the run expansion in terms of your commuting charges, and the transfer matrix commutes with itself for different values of the spatial parameter. So it's a similar structure to what we had before, but now we can incorporate the boundary conditions, right? And then a final thing that becomes important later is kind of how you reduce the charges, right? So for the moment, I am taking the UN and UN bar and saying, okay, these were our canonical conjugates. For the moment, we're going to upgrade them to a more general set of fields, Qn and Rn. So on the next slide, we'll see why that's important. So as before, we can expand the transfer matrix in powers of the spatial parameter. And from this, you can construct the Hamiltonian as a quotient of Q1 and Q0. And this gives us a very interesting system, right? So you have the usual terms, the usual sum over your field. But now you've introduced these boundary terms, parameterized by alpha plus and alpha minus. But in order to reduce this back to a system that we can use, we can't take Qn Rn to UN bar. That actually doesn't work. Instead, we need to use a -1 bar. Okay, so that's a non-local reduction, and this gives you an interesting lattice system that actually has gain and loss, right? So let's look at this. Q dot of -n is proportional to Q minus n. So that's gain in the one node, and then loss in the second node. Q dot n is proportional to minus Qn, right? So we have gain and loss being introduced into the system. We have a way of constructing the conserved charges. So we kind of have something that we want. This is completely integrable. It is an oligomer of an arbitrary size, and there's balanced gain and loss. So this is fantastic, right? And the way that you can think about this is it's a folded lattice. So you just take your nodes and you fold them over, and then the gain and loss nodes interact with each other, and right, all the nodes kind of interact with its pair node on the opposite end. But what we're kind of interested in are the special lower dimensional cases, so n equals 3 to 4. Just because these models are nearest neighbor models, which are more physically plausible. So we'll start with the dimer and then hopefully get to the trimer and quadrimer. What's nice about the n equals 2 case, like, okay, we're not interested in the n equals 2 case, we want to upgrade, but let's use it as a starting point and look at the dynamics. Because we asked, okay, we want a system where there's PT-symmetry breaking occurring, and where restoration is occurring, right? So we want to see, do the nonlinearities actually arrest the blowup? So let's focus on the dimer, right? This is our simplest model, and the linearization about uv equals 0 is clearly non-Hermitian, right? This is your linearized, let's call this Hamiltonian, and clearly does not satisfy the hermiticity condition. Okay, so blowup is observed for gamma greater than 1. But now let's see what happens when we introduce the nonlinearities. And you can solve the system exactly, right? You use the same Stokes coordinates that we introduced for the standard dimer, and what you end up with is an alternative Hamiltonian expression for the system in terms of capital X, with some odd-looking potential. So in the case gamma equals 0, right? So if you set it equal to 0, then you end up with an elliptic integral. That is something you can solve. If you make gamma non-zero, then it's not really solvable anymore, only approximately. But the point is, you can clearly see a bifurcation occurring. So at gamma equals 0, you have a parabolic potential. But as gamma increases past some critical value, it forms a double well potential that actually, it induces bifurcation, kind of restricts the phase space that your solutions can access. So thus in the Stokes coordinate, if we invert it back to U and V, we can look at how the amplitude and phase behave. So at gamma equals 0, you have these well-behaved oscillations, right? So this is for U and V. That's the amplitude. And that's the phase, right? As we increase gamma, we observe this kind of unbounded increase in the period. So if you define the period of oscillation as t, this is going to infinity, right? And it goes to infinity up to this gamma critical. Past that point, we observe a change in the dynamics, right? So after the bifurcation, we have t going to the period going to 0 as gamma increases. And there's also this restriction of the phase that occurs. Like notice here, in the initial phase, the range stays the same. Past the critical point, the range decreases for the phase, right? So there is a clear bifurcation happening. And this is a type of PT-symmetry restoration, right? So that's fantastic. Oh, hi.
Sorry, Frank. I'm afraid I missed what gamma was. Is that related to those boundary conditions that you imposed?
Yes, that's correct. Let's go back to the system. Where was it? Right. So alpha plus and alpha minus, those are the boundary terms, right? They're coefficients for the boundary terms. And in the final step, after doing the reduction, we specify alpha plus equal to I gamma and alpha minus equal to minus I gamma.
Oh, I see. Thanks.
Cool. Right, yeah, so gamma, that parameterizes the gain and loss. And in our case, with the Robin bound, it parameterizes the boundary conditions as well. So the boundary conditions are what you're using to introduce the gain and loss into the system. All right. Yes, so I've talked about the PT-symmetry restoration, and that's good news. So in conclusion, we have successfully constructed a family of integrable oligomers, so high-dimensional networks of optic fibers, with the properties that we want. Right, there's PT-symmetry restoration. The solutions don't blow up. So there are some follow-up questions. Firstly, right, we've used all this formalism to construct some optic fiber models, but we actually need to show also that these describe real systems. So you can proceed, for example, the way we did with the paraxial approximation. You come up with a system and you try to find its envelope equations. That's one way to do it. You can look at singular perturbation methods. So that's kind of one of the next steps. And then there's also a question about the reduction, because I mentioned that, okay, I upgraded QN and RN, and I couldn't upgrade it or reduce it down to UN and UN bar. But what I'm interested in seeing is whether you can construct a model like this and still retain the integrability. That's kind of an open question. But at this point, I have pretty much covered everything that I wanted to. So thank you to all for listening, and I open to the floor for questions.
Right. Thank you so much, Frank, for this brilliant presentation. So we move to questions now. If you have question, you unmute and ask your question. But just before that, before you go, I give the floor to the audience. Frank, can you please explain, for those who are unfamiliar with the PT-symmetric system, could you briefly explain why they are important in modern physics?
Yes, so let me see if I can find a nice slide for this. Okay, so We can talk about this in terms of quantum mechanics and also in terms of classical mechanics. So in quantum mechanics, PT-symmetry is a really big deal because, with your postulates of quantum mechanics, kind of it's really fundamental that the Hamiltonian should be Hermitian. But PT-symmetry says actually this is not true in general. You can have a Hamiltonian that is PT-symmetric. Let's call this HPT, right? So that's a PT-symmetric Hamiltonian. It does not need to be Hermitian.
Okay.
It's not Hermitian. Sorry, that's a dagger. And at least for certain ranges of your PT-symmetric parameters, that Hamiltonian can still have real spectra, right? So the system can still have real energies. So what it's kind of pointing at is that there's you can actually make the fundamental postulates of quantum mechanics, you can make them more lax. It's not actually that restrictive. That's in quantum mechanics. In classical mechanics, what this allows you to do is have a really rigid analytical structure for systems with gain and loss, right? So it's really nice for these optical coupler systems, for example, because you can add gain and loss, right? So the system is, in a sense, non-conservative, but you can still assign a Hamiltonian to it, regardless, right? That's completely conserved in the phase space. All right, so the phase volume is conserved. It's kind of, firstly, you can, so you can talk about these experimental systems with gain and loss completely analytically. They have very nice properties, and also some very specific practical applications come out of the PT-symmetry. You can use it to construct very nice devices. Like probably one of the coolest examples is that you can use PT-symmetric models to describe, for example, like invisibility cloaks. I don't actually know how this works, but you can talk about PT-symmetry as a tool to actually like set up some cloak that renders some object behind it invisible. That's just one of the kind of like flashy applications. Is you can do you can make an invisibility cloak with the PT-symmetric system, but it also applies to various electronics, so sensing devices. You can also talk about Bose-Einstein condensates with gain and loss. And as we've talked about, in optics, you can use it to talk about systems where there's energy going in and out. Yeah, so that is my short answer to the question. Does that answer your question?
Yes, yes, you answered my
All
question.
right.
Thank you so much, man. So the audience, can we have 2 questions from the audience? Okay. Any question? You can just unmute and ask your question. All right.
Maybe
Like,
one more quick
okay.
question, Frank. So your boundary matrices, I think you chose them to be diagonal, kind of, right?
Yes.
Is that just for simplicity, or is it the most general thing allowed by integrability?
The short answer is no, it's not the most general K matrix you can construct. You can actually have off-diagonal terms, but what you end up with are these boundary. It's not really clear what the boundaries or what type of boundary conditions they are. The main paper that I'm referencing is by Cordelier and Crump. And they study the most general case of this K matrix. Yeah, so I used to have the K matrix, the reflection equations in here. But yeah, for the diagonal case, you can explicitly show that's an open boundary condition. The interpretability of the off-diagonal case, I'm not sure about.
Okay, thanks.
All right. If there's no question, then we will end here.